In this lesson, we're going to focus more on some of the properties of logarithms and also start getting into some deeper logarithmic equations. So to start out with, the property of equality for logarithmic functions. If we have log base b of x equal to log base b of y, that is true if and only if x equals y. And guys, notice this little arrow right here. This goes both ways. Later in this unit, we will have situations where we have an equation and we take the log of each side of the equation to solve the problem. So you need to understand that this property is something that it's an if and only if statement. It works in both directions. All right, so to apply this, the first equation, it says solve each equation. Log base 10 of t squared minus 6 equals log base 10 of t. Because these are equal to each other and they have the same base, that is only true if what's inside of them are both equal. Another way we can look at this is we can apply the property of equality for exponential functions. In other words, what we can do is we can base this up. I know this is really weird, but we have some base raised to the x equal to some base raised to the y. That is true if and only if x is equal to y. But it also holds true in the other scenario. If we have x is equal to y, we can come in here and as long as we use the same base, we can base it up on each side and it's still an equivalent equation. So that's another way we can look at this right here is we could come in here and say, okay, well, since the base is 10, we can 10 it up on each side. I call it basing it up. And what that allows us to do is use the property from the previous lesson. The exponential function undoes the logarithmic function, and it's kind of like they cancel each other out because that's the whole point. And then this just pops out. T squared minus 6 is equal to t. Now, some of y'all will not write that step out. You might just apply the property of equality and go, oh, okay, well, I've got a log equal to a log. They have the same base, so their answers have to be equal, and that's fine also. At this point, we have a quadratic equation. So the first step is to set this equation equal to 0. So we're going to subtract t from each side, and let's make sure we put it in that descending order. So we have t squared minus t minus 6 is equal to 0. This is an easy trinomial to factor. The two numbers that multiply to negative 6 and add to negative 1 would be positive 2 and negative 3. So our factors would be t plus 2 and t minus 3. We would then set each factor equal to 0 and solve. So we have t plus 2 equals 0, t minus 3 equals 0. So we have t is equal to negative 2, and t is equal to 3. So going back to our last lesson, recall that logarithmic functions have a domain of only positive real numbers. Because they are the inverse of exponential functions, a logarithmic function's domain is restricted from 0 to infinity, not including 0. So if we go back to our lesson and we look at this, we have to be very careful. We always have to make sure we check for extraneous solutions. We've solved the equation beautifully, but we have to check and make sure that if we were to substitute these answers back inside to that logarithm, that it would make that expression positive. So looking at negative 2, if we were to substitute negative 2 into the second part right here, so that would be log base 10 of negative 2. That would not be possible, folks, because we can't take the log of a negative number. So I don't even have to substitute the other part because I know that it would give me an undefined value. But if we were to substitute 3 back into both of them, 3 squared is 9, 9 minus 6 is 3, so that side would be good. That would have given me log base 10 of 3. And if I substitute this side, that would also be log base 10 of 3, and you can even see that they come out to be equivalent. So in this case, we only have one solution. The negative 2 is extraneous, and the 3 is our answer. So when solving log equations, you always have to check your answers and make sure if you were to substitute them back in, that it would make the expression we're taking the log of a positive expression. All right, so pause the video, try the next one, and when you're done, start the video back. All right, since this is log base 3 of some expression equal to log base 3 of some expression, we can just use our property of equality and set those expressions equal to each other, which would give us 3x minus 5 is equal to x plus 7. You could also think about it as basing it up on each side. If I 3 it up over here and 3 it up over here, those would undo each other, and we still would get that 3x minus 5 equals x plus 7. This is just a linear equation, so we would subtract x from each side and add 5 to each side. We get our variables on one side and our constant terms on the other. So 3x take away x is 2x, and 7 plus 5 is 12, and we would divide each side by 2, and we get that x is equal to 6. If we substitute 6 back in, 3 times 6 is 18. 18 take away 5 is 13, so that's good. It's a positive number. And 6 plus 7 is also 13. It's a positive number, so we're good to go. All right, the next part of our lesson is about some of our properties, and these are very special properties, so we actually call them the laws of logs, or the laws of logarithms. The first one is the product property. What the product property tells us is if we have log base b of m times n, that is equal to log base b of m plus log base b of n. And I want you to think about your exponent rules. Remember, a logarithm is an exponent. And the fact that when we multiply like bases, we add our exponents, has a connection with this property. So anytime we have the log of a product, we can expand it into the log of each part of that product, each factor, as sums. So the next one is the quotient property. If we have log base b of m divided by n, that is equal to log base b of m minus log base b of n. And again, think about it. When we divide like bases, we subtract those exponents. The third one is the power property. So the condensed form is if we have log base b of m to the p power, that is equal to, we can take this power right here, this p, and we can drop it down as the coefficient. So it is equal to p times log base b of m. Or vice versa, if we're in the expanded form, we can take that coefficient that's in front of that logarithm and pop it back up as the power. So it depends on what we're doing and when you're needing to condense versus expand. Okay, so for this next part of our lesson, what we're going to do is just practice using those laws of logs to expand or condense a expression. So these first couple, it says, rewrite each expression in a form with no logarithm of a product, quotient, root, or power. So it's giving us the condensed form, and we want to expand it. So with this first one, we don't have any exponents yet. So what we're going to do is break up this product. And we would say, well, this is equal to log base 3 of x plus log base 3 of the square root of y. Because remember, if you have a product, we can break that up into a sum. Well, we know that roots are the same thing as fractional exponents. So we can rewrite this second part right here, this log base 3 of the square root of y, as log base 3 of y to the 1/2. Now we can use our third law of logs, our power property, and we can take that power that's up here on this y, that exponent, and drop it down in front as the coefficient. So this is log base 3 of x plus 1/2 times log base 3 of y. And that's as far as we can go with this. And I know right now you're like, why in the world are we doing this? But it's a skill, and I promise it has importance. So you just have to hang in there, learn the skill, and you'll see why it's important later on. Let's look at the next one. All right, so this one's got a product in the numerator, and then it also has a quotient because it's dividing the numerator by the denominator. So let's break it up. So we would say, and notice this one doesn't have a little subscript. That's okay. It's actually, when you don't see the subscript, it's base 10. We'll be talking about that in our next lesson. But if it doesn't have a subscript, don't worry, just write it out. So this is log of x cubed plus the log of the square root of x minus 1. And then because this 3x plus 4 is in the denominator, we're dividing by it. So we'd say minus the log of 3x plus 4. All right, again, we don't want any roots or powers. So this 3 right here, it's good to go. We can go ahead and drop that down in front. But for the second term, we're going to have to rewrite that square root as a power. So this is going to be 3 times the log of x plus the log of x minus 1 raised to the 1/2 power. Anytime we have a root, we got to rewrite it as its equivalent fractional exponent. And then minus the log of 3x plus 4. And then last but not least, we can also drop this power of 1/2 down right here. Oops. So we end up with 3 log of x plus 1/2 times the log of x minus 1 minus the log of 3x plus 4. Now sometimes I'll have students try to go further with this. They're like, oh, but Ms. Sauter, we still have a product. We have a product over here of 3 times x. We cannot break that product up because it's also attached to this plus 4. The only rules we have is if we have only a product or only a quotient or a power, we can move those things around. But if we have an expression that has multiplication and addition or division and subtraction, we cannot break that apart. So this is done. This is as far as we can go. All right, so look at this part. It says evaluate the expression. So here's where we're going to use those laws of logs to clean this up. Then we'll be back to a problem like we had in our previous lesson, and we can evaluate the logarithm. So this first one, we do not have any coefficients. If you have coefficients on your logarithms, you must get rid of those first before you can add the logarithms to make it a product or subtract the logarithms to make it a quotient. So in this case, we can go ahead and pop this together. This is going to be log base 10 of 2 times 5. So we're going from the expanded form back to the condensed form. That then gives us log base 10 of 10. Now from what we learned in our previous lesson, we're going to evaluate this logarithm. 10 to what power equals 10? And that gives us 1. This is also one of our properties that we talked about in our previous lesson. Anytime we have log base b of b, the answer will always be 1. All right, looking at the next one, we actually have a coefficient on the second expression, on the second logarithm. So we have to take care of that coefficient before we can condense these logs. So this is going to give us log base 5 of 100 minus log base 5 of 2 to the second power. So let's clean that up. Log base 5 of 100 minus log base 5 of 4. Now that we've gotten rid of the coefficients, we can condense this. When we subtract these two logarithms, we can make it one logarithm by dividing the 100 and the 4. So this is log base 5 of 100 divided by 4. So this becomes log base 5 of 25, and then we evaluate it. 5 to what power would give us 25? And the answer is 2. All right, the next one is not numerical in nature. It's got variables in it again, but we are doing the opposite of what we did on the other side of this lesson. We are now going to condense it. It says rewrite the expression as a single logarithm. So we're going to use the same steps we did in the top problems. The first step is we always have to get rid of any coefficients. We cannot add or subtract logarithms if it has coefficients. So all these coefficients are going to pop back up and become the powers. So the next step is then if any of them are fractional exponents, we will normally go ahead and change that over to a radical. So you can rewrite this, and just the middle one, we're going to rewrite that as the cube root. That's going to give us log base 2 of x to the 4th minus log base 2 of the cube root of x squared plus 1, and then plus log base 2 of x minus 1 squared. Now that we've taken care of all of that, we can put it together. Anything that's being subtracted goes in the denominator, and anything that's being added goes in the numerator. You also could use your commutative property here and rearrange these terms. You don't have to, but you can. So ultimately what we get right here is we have log base 2. In the numerator, we're going to have x to the 4th and the x minus 1 squared because it was also being added. The only part being subtracted is that middle term. And then we'll have divided by the cube root of x squared plus 1. And that is our final answer. It's that condensed logarithm. Okay, so now we're going to come back to equations, and we are going to apply these law of logs to solve equations. All right, one of the biggest mistakes I will see students make is they'll go, oh, this has a base of 3. So I can just come in here and I can 3 this part up, and I can 3 this part up, and I can 3 this part up, and all those logarithms cancel out, and I got 6 minus 16 equals x, and oh my goodness, I can't even begin to tell you how wrong that is, so please do not do that. That is incorrect. The only way that we can base up each side or apply the property of logs is if we condense each side to be a logarithm equal to a logarithm. So the first step is you always condense each side of the log like what we did above. So if it has any coefficients, we pop those back up as the exponent. So that's what we're going to start by doing. So with this first one, we're going to have log base 3 of 6 squared minus log base 3 of 16 to the 1/4 power equals log base 3 of x. Then we need to evaluate this. So that is log base 3 of 36 minus log base 3 of 2. And folks, that's why you really need to be studying your perfect squares and cubes and your powers of numbers. 16 to the 1/4 power is the 4th root of 16, which is 2. We need to be able to recognize that, or at least break it up over to the side. Equals log base 3 of x. Now that we have cleaned up each logarithm and we don't have any coefficients left, we can now condense it to be one logarithm by subtracting. And remember, when we subtract two logarithms, it becomes a quotient. So this becomes log base 3 of 36 divided by 2 equals log base 3 of x. So that's log base 3 of 18 equals log base 3 of x. And then property of equality for logarithms, if we've got a log with the same bases equal to each other, then the insides must be equal and 18 must be equal to x. Or you can apply your exponential function property of equality and base it up on each side, and then they cancel each other out, and we get 18 equals x. And if you checked 18, it's good because it makes you have the log of a positive number, so we do not have extraneous solutions. All right, the next one's very different because the next one only has logarithms on one side. So anytime you have an equation where some terms have logs and some terms are just numbers, what you want to do is you want to get all the log terms on one side and your constants on the other side. Then, on the side with your logarithms, condense it to be one logarithm. So in this case, we're going to check, do we have any coefficients? We don't. So we're going to add these two logs, which is going to give us log base 10 of x times x plus 3 equals 1. Okay, so there's two ways that you can work this out from here. Now I'm going to go ahead and clean it up real quick. That's log base 10 of x squared plus 3x before I start to work it out. The easiest way to do it is just to base it up. That's why on these other problems I've been showing you the basing it up. It's the quickest, least amount of work, least amount of thinking. If I have an equation, as long as I base it up on the same side, I know that's so weird, but if I tin it up on both sides, it's still equivalent. Well, what happens is on the left-hand side, we have that property we learned in our previous lesson. If we have a base raised to log of the same base of x, it gives us x. And that's because an exponential undoes a logarithm. They are inverses. So ultimately what happens here is this 10 raised to log base 10, it's like they cancel each other out. So we are left with just x squared plus 3x. However, on the right, nothing undoes each other, so you actually have to do 10 to the first power, which is 10. We then have a quadratic equation, so we would set the quadratic equation equal to 0, x squared plus 3x minus 10 equals 0. We would factor it, so we'd have x minus 2 times x plus 5 is equal to 0, and we would solve. So we get x is equal to 2 and x is equal to negative 5. When we substitute 2 back into this logarithm, we're good, and the second logarithm, we're good. However, if we substitute negative 5 into that first logarithm, we're not good, so there's no reason to even check the second one. If it doesn't work in any of them, it's not going to work. So in this case, we only have one answer. The other one is extraneous. Another way that you could have done it is when you got to this step right here. So I'm going to write this over to the side. This one takes a little bit more thought process. But when you get here and you have log base 10 of x squared plus 3x equals 1, because it's not a log equal log, you can't just drop the log out. So you can either 10 it up on each side like we did in the first method, or you can change it back to exponential form. You say, what is our base? Oh, it's 10. What is the exponent? It's 1 equals our answer, which is x squared plus 3x. Just from that lesson, log base b, or the base is a subscript of the answer equals the exponent, and when you put it back in exponential form, it's the base raised the exponent equals the answer. And you'll probably recall from yesterday's lesson, you do that kind of little loop there, and then it's equal to this. And notice once you do that, you have the exact same equation as when I 10'd it up on each side. I just find it's easier to 10 it up on each side and be done with it. Okay, so what I would like for you to do now is I would like for you to try the next two problems. They are very similar to problems A and B. And then in class, we will go through these problems together and work on our practice.